Respected Professor Jagdish Joshi sir, the Director of UGC Malavya Mission Teacher Training Center of Gujarat University, Dr. Dilip Vasawa sir, Course Coordinator of UGC Malavya Mission Teacher Training Center of Gujarat University, and dear participants. I, Dr. Paresh Patel, thank UGC Malavya Mission Teacher Training Center of Gujarat University for giving me an opportunity to connect with you and deliver my session on molecular symmetry. I thank Professor Jagdish Joshi sir, Professor and Director of UGC Malavya Mission Training Center of Gujarat University, Dr. Dilip Vasava sir, Course Coordinator and team members. First online refresher course was arranged in the year 2018 to 19 and about 2,500 participation have attended it. So this is the beauty of this refresher course. So dear participants, the topic of today's discussion is molecular symmetry. The correspondence of a figure with reference to plane, line, and point of a symmetry. So this is the exact definition of molecular symmetry. And this type of the symmetry arise in our molecule is known as a molecular symmetry. So anyhow, the correspondence of a figure with reference to plane, line, or point of a symmetry. Thus, a circle is a symmetrical about any diameter. The term symmetry has become synonyms to the beauty because the nature has made most of its creation symmetrical. As for example, the sun, planets, animals, and plants. Scientifically speaking, an object is said to be symmetrical if it can take up more than one equivalent orientation. For examples, let us consider hydrogen molecule. If we consider any imaginary axis, and along that imaginary axis if we rotate hydrogen molecule around 180 to get the equivalent orientation position. So that type of the symmetry arises in a hydrogen molecule. Symmetry is all around us and is a fundamental property of nature. The beauty of Taj Mahal and Eiffel Tower is due to their symmetry. Symmetry is when an object has two or more equal sides when split in half or in smaller pieces. This is the butterfly has line of symmetry. In case of the water molecule, the shape of the water molecule is a V-shaped. If we image a imaginary axis in the water molecule and if we rotate these molecules along this imaginary axis around 180 to get the equivalent orientation position. So this is a classical examples of molecular symmetry. We already discussed that the correspondence of a figure with reference to plane, line, or point of a symmetry. And this type of the symmetry arise in our molecule is known as a molecular symmetry. Symmetry elements and symmetry operations. These two terms are the most important in the symmetry. Point, line, and point. Point, line, and planes. These are known as a symmetry elements. And the symmetry operation is carried out with respect to plane, line, or point to get the equivalent orientation position. So this process can be recognized as a symmetry operation. Identity, proper axis of rotation, mirror planes, center of symmetry, improper axis of rotation. These are the symmetry elements and their related symmetry operation. So let us start first with the identity. So identity is a symmetry element and all molecules have identity. This operation leaves the entire molecule unchanged. It means each and every molecule consists identity symmetry elements. And if we operate identity symmetry operation on any molecule, molecule remains as is as it is. There is no change. Second symmetry element is proper axis of symmetry. And proper axis of symmetry can be symbolized by Cn. N is equal to order of axis, where N represents order of axis. In case of, if you rotate any molecule around 180, so in that case, order of axis n is equal to 360 by 180. So in that case, n is equal to 2, means order of axis for that molecule is equal to 2. If you rotate any molecule around 120, so in that case, order of axis is equal to 3. If we rotate any molecules around 90, so in that case, order of axis is equal to 4. If you rotate any molecules around 60, so in that case, order of axis is equal to 6. And if you rotate any molecule around infinite, so in that case, order of axis is equal to infinite. So, proper axis of symmetry. So, if we rotate any molecule around along any imaginary axis to get the equivalent orientation position. So that type of the symmetry can be recognized as proper axis of symmetry. As for example, first molecule is a water molecule. In case of water molecule, the shape of the water molecule is V shape. Now, this is the imaginary axis, and if we rotate this water molecule along this axis around 180 to get the equivalent orientation position. So, C2 is a symmetry element in case of the water molecule. Now, if you operate symmetry operation on water molecule, so what will happen? If you rotate these molecules along this axis around 180, so to change the position of these hydrogens, so that symmetry operation can be represented as a C21. So, dear participant, remember that C2 is a symmetry elements and C21 is a symmetry operations. So, water molecule consists identity symmetry elements as well as C2 symmetry element. And if we operate C2 symmetry operation on water molecule to change the position of the hydrogens. In case of ammonia molecule, the shape of the ammonia molecule is a pyramidal. So this one is the imaginary axis, and if we rotate these ammonia molecules along this imaginary axis around 120 to get the equivalent orientation position. So C3 is the symmetry element, and C31, C32, C33, these are the symmetry operations. So if we operate or if we rotate these ammonia molecules along the imaginary axis around 120 to change the position of the all the three hydrogens, so that symmetry operations can be represented as a C31 if it is a clockwise, and if it is anti-clockwise, that can be represented as a C31 inverse or C3 minus. In case of the two-fold axis of symmetry, that is for order of axis is equal to 2. If we operate symmetry operation around 180 to change the position of the hydrogens, so that represented this that symmetry operations can be represented as a C21 and C22. In case of trigonal planar molecule, as for example BF3 molecule, or we can say this is a trigonal polar molecule. So this one is the imaginary axis, and with the help of this imaginary axis, if we rotate these molecules along this axis around 120 to get the equivalent orientation position. So here n is equal to, so here n is equal to 120, n is equal to 360 divided by 120 is equal to 3, means order of axis is equal to 3 for this axis. Now in case of 1, 2 and 3, if we rotate these molecules along this axis around 180 to give the equivalent orientation position. So in case of trigonal planar molecule, one axis is C3 and C3 is perpendicular to 3C2s according to the symmetry elements and symmetry operations. According to the rules and regulations of the molecular symmetry, higher order axis proceed first as a main principal axis. So in this case, C3 is higher than C2. So C3 can be considered as a main principal axis, and C3 is perpendicular to 3C2s. So C3 is the main principal axis and 3C2s are the subsidiary axis. In case of the cyclobutane, this is the imaginary axis, and with the help of this imaginary axis, if we rotate this molecule along this imaginary axis around 90 to get the equivalent orientation position. So in this case, order of axis n is equal to 360 by 90 is equal to 4. So C4 is a symmetry element, and if we rotate these molecules around 90, so that symmetry operation can be represented as a C41. So different symmetry operations, C41, C42, C43, C44, these are the symmetry operations. In case of cyclopentane molecule, this one is the imaginary axis, and if we rotate these molecules along this imaginary axis around 72 to give the equivalent orientation position. So here n is equal to 360 by 72 is equal to 5, means order of axis for the cyclopentane molecule is equal to 5. Now in case of the cyclopentane, if you rotate these molecules along this axis, this axis, this axis, this axis, and this axis around 180 to give the equivalent orientation position, it means cyclopentane molecule consists one main principal axis as a C5, and C5 is perpendicular to 5C2s, and the order of axis of the main principal axis is C5. So C5 is higher than C2. So C5 can be considered as the main principal axis, and 5 C2s are the subsidiary axis. Benzene molecule. In case of the benzene molecule, this is the imaginary axis, and if you rotate these molecules along this imaginary axis around 60 to get the equivalent orientation position. So order of axis for the benzene molecule is equal to 360 divided by 60 is equal to 6. So order of axis for the benzene molecule is equal to 6. So if we operate in case of the benzene molecule, if we rotate these molecules along this axis, this axis, this axis, this axis, this axis, and this axis at 180 to give the equivalent orientation position. So in case of the benzene molecule, C6 is perpendicular to 6C2s. So C6 is a main principal axis and 6C2s are the subsidiary axis. If we operate C6 symmetry operation on a benzene molecule, so that symmetry operation can be represented as C61, C62, C63, C64, C65, and C66. Now this is BF3 molecules. In case of the BF3 molecule, if we rotate these molecules along this imaginary axis around 120 to change the position of the boron fluorine bond, and that symmetry operation can be represented as a C31, again 120, that is known as C32. Two times clockwise rotation is equal to one time anti-clockwise rotation in case of the BF3 molecule. So this is the C31, C32, and C33. In case of the NaCN4, NaCN4, the structures of the NaCN4 minus 2 complex is a square planar. So main principal axis for NaCN4 minus 2. If you rotate these molecules along this axis around 90 to get the equivalent orientation position, means order of axis for this molecule is 4. So C4 is a main principal axis, and 1, 2, 3, and 4. 4 C2s are perpendicular to the main principal axis C4. In case of the benzene, we already discussed that main principal axis is C6 and C6 is perpendicular to 6 C2s. Now in case of PtCl4 minus 2 complex, this one is the imaginary axis, and with the help of this imaginary axis, if you rotate these molecules around 90 along this imaginary axis to get the equivalent rotation position. So this main principal axis is C4, and in case of the PtCl4 minus, C4 is perpendicular to 4 C2s. Another molecule is iron pentacarbonyl. In case of iron pentacarbonyl, the main principal axis is C3. Why? If we rotate these molecules along this axis around 120 to get the equivalent orientation position. We know that the shape of the FeCO5 molecule is a trigonal bipyramid. So if we rotate these molecules along this axis around 120 to get the equivalent orientation positions. If we rotate these molecules along this axis around 180 to get the equivalent rotation position. So in this case, C3 is perpendicular to 3 C2s. Now, third symmetry element is the plane of symmetry, and plane of symmetry can be symbolized by sigma. Now, what is plane of symmetry? We have to image a plane, and with the help of that imaginary plane, we can bisect the molecule in such a way that one part is the mirror image of the another part of the molecule. Plane of symmetry can be classified into three categories. First one is vertical plane of symmetry. Second one is horizontal plane of symmetry. And third one is diagonal or dihedral plane of symmetry. Now, first one is vertical plane of symmetry. Vertical plane of symmetry can be symbolized by sigma v. Now, what is vertical plane of symmetry? If plane is parallel to main principal axis, so that type of the symmetry, what that type of plane of symmetry can be recognized as a vertical plane of symmetry. So dear participant, if the main principal axis is parallel to the plane, so that type of the plane of symmetry can be recognized as a vertical plane of symmetry. As for example, water molecule, this is the main principal axis of water molecule, and water molecule consists two types of the vertical planes. Why vertical planes? Both these planes are parallel to main principal axis. One plane is a sigma xz plane, another one is sigma yz plane. Sigma xz plane can also be recognized as a molecular plane. Now, water molecule consists two types of the vertical planes, that is sigma Vxz and sigma Vyz. These are the symmetry elements. And if we operate sigma Vxz symmetry operation, so there is no change in the position of the hydrogen. Why? The sigma xz plane is a molecular plane. But in case of if we operate sigma Yz symmetry operation on the water molecule, to change the position of the hydrogen, because this plane can bisect the molecule. So in case of water molecule consists two vertical planes. One is sigma Vxz, another one is sigma Vyz. If we operate sigma Vyz symmetry operation to change the position of the hydrogens, but in case of if we operate sigma Yz symmetry operation, so there is no change in the position of the hydrogens. Another examples for the vertical plane of symmetry is ammonia molecule. Ammonia molecule consists three vertical planes. Ammonia, the shape of the ammonia molecule is a pyramidal, and all the three planes are parallel to the main principal axis. So ammonia molecule consists three vertical planes: sigma V1, sigma V2, and sigma V3. If you operate any symmetry operation to change the position of the another hydrogens of the ammonia molecule, Second type of the plane of symmetry is horizontal plane of symmetry. Horizontal plane of symmetry can be symbolized by sigma h. Now, what is horizontal plane of symmetry? If plane is perpendicular to the main principal axis, so that type of the plane of symmetry can be recognized as a horizontal plane of symmetry. In case of the BF3 molecule, we already discussed that in BF3 molecule, main principal axis is C3 and three C2s are perpendicular to the main principal axis, and this plane is also perpendicular to the main principal axis. So horizontal plane of symmetry means plane is perpendicular to the main principal axis. So this is a classical examples of the horizontal plane of symmetry. In case of PF5 molecules, PF5 molecule, this one is the main principal axis, and the shape of the PF5 molecule is trigonal bipyramid. So in this case, this plane is perpendicular to the main principal axis. Means this is an example of horizontal plane of symmetry. So if we operate sigma s symmetry operation in case of PF5 molecule, so what will happen? There is no change in the position of the F1, F2 and F3, but to change the position of F4 and F5, because this one is the horizontal plane of symmetry. So if we operate sigma s symmetry operation to change the position of F4 and F5. Third type of the plane of symmetry is diagonal plane of symmetry or dihedral plane of symmetry. In case of diagonal plane of symmetry, we have to image a plane, and that plane can bisect the main principal axis and situ in such a way that one part is the mirror image of the another part of the molecule. So that type of the plane of symmetry can be recognized as diagonal plane of symmetry or dihedral plane of symmetry. This is an example of the alene molecule. So in case of the alene molecule, this one is the C2 and this one is the main principal axis C2. So we have to image a plane, and that can bisect the molecule in such a way that one part is the mirror image of the another part of the molecule. So benzene molecule consists sigma H symmetry, a plane of symmetry. Then water molecule consists two vertical planes that we already discussed. Now fourth type of the symmetry element is center of symmetry. Center of symmetry can be symbolized by I. This is an imaginary point in the center of molecule through which the reflection of each atom can be carried out to result in its coincidence with an equivalent atom. It means in case of center of symmetry, we have to image a point, and with the help of that imaginary point, we have to inversify each and every atom of the molecule, so that type of the symmetry can be recognized as center of symmetry. And if we operate center of symmetry to the molecule to change the position of the molecules. This is the symmetry operations of the inverse center of inversion. So which can inversify that molecule. So benzene molecule consists I and trans dichloroethylene. If we operate center of symmetry to the trans dichloroethylene to change the position of both this chlorine and hydrogens. Fifth symmetry element is the improper axis of symmetry or rotation reflection axis of symmetry. And improper axis of symmetry, rotation reflection axis of symmetry can be symbolized by Sn. Sn is a symmetry element. This is an axis passes through the molecule on which the molecule has to be rotated by 2 pi by n angle and then reflect on a plane perpendicular to the rotational axis to attain an equivalent orientation. The axis of proper rotation is represented as Sn. So Sn is equal to Cn plus sigma h. It means it is a combination of proper axis of rotation and reflection through the horizontal plane. So what is improper axis of symmetry? First of all, we have to rotate the molecules around theta and reflection through the horizontal plane of symmetry to get the equivalent orientation position. This is the improper rotation in the tetrahedral molecules. This is S1 and it is S2 improper rotation. In case of the trans-dichloroethylene, if we rotate the trans-dichloroethylene around 180 and then reflect through the horizontal plane to get the equivalent orientation position, so that molecule consists improper axis of symmetry. And symmetry operation can be represented by SN1, SN2, S, S21 and S22 in case of trans-dichloroethylene. Dear participant, previously we discussed about the general introduction about the molecular symmetry. Now second part of our molecular symmetry is the point group. So how to assign point group in a molecule, that is most important. So point group can be defined as the collection or combination of symmetry elements, all possible symmetry elements and their symmetry operation which meet a point is known as a point group. Now how to assign a point group to the molecule? So according to the Schoenflies method, we can assign a point group to the molecule. For that, we have to follow a chart, and with the help of that chart, we can assign a point group to that molecules. So first of all, we have to make a question that is a molecule linear or non-linear? Then C infinite V, D infinite H point group may be present. If it is non-linear, then we have to make a question that so first of all, we have to make a question that is a molecule linear or non-linear. If it is non-linear, then we have to make another question. Multiple harder axes are present. Yes, then TD, OH and N. And no means we have to make another questions. Any proper improper axis are present. In case of molecule is a linear, then C infinite V or D infinite H point group may be present. If yes, in this case, proper and improper. As in case of proper axis, we have to make a question that Cn isn't perpendicular to and Cn is perpendicular to NC2. No. Then we have to make a question C1, Cl or Cs. Sigma H is present, Cs, I is present, Ci, both are present, right? C1, both are absent, then C1. Cn, Cnv, Cnd and Cnh? If yes, sigma H is present, DNH, sigma V is present, then DNV, sigma D is present, then DND and Dn. All are absent, then Dn. In case of Cn, sigma H is present, then CNH, sigma V is present, then CNV, sigma D is present, then CND and all are absent means Cn. So dear participant, first of all, how to assign a point group to the molecule? First of all, we have to make a question that is a molecule linear or non-linear. If it is linear, then there is no problem. C infinite V, D infinite H molecule may be present. If sigma V is present, then C infinite V point group may be present. Sigma H is present, then D infinite H molecule may be point group may be present. Now, in case of the non-linear, if our molecule is non-linear, then we have to make a question: multiple harder axes are present. If yes, then we have to make a questions TD or OH. Sigma D is present, then TD. Sigma H is present means OH. Otherwise, we have to go for OH. Any proper improper axis? Yes. Improper axis means SN. Proper axis means we have to make another question: Cn perpendicular to NC2s. If it is yes, then Dn, Dns, Dnd or Dnd. If sigma H is present, then point group is DNH. If sigma V is present, then that point group is DNV. If sigma D is present, then point group is DND. If sigma H, sigma V, sigma D all are absent, then Dn. Similarly, in case of Cn doesn't perpendicular to NC2, in that case point group may be Cn, Cnh, Cnv or Cnd. If sigma H is present, then point group is Cnh. Sigma V is present, then point group is Cnv. Point group sigma D is present, then point group is Cnd. Sigma H, sigma V, sigma D are absent, then point group is Cn. So dear participants, first of all we have to make a first question, linear non-linear, and then we have to go for the linear, then sigma V or sigma H. Otherwise we have to go for the next questions. So let us start with the first example is the carbon dioxide. Is it linear or non-linear? This molecule is a linear. So is a molecule linear or non-linear? So this molecule is a linear. So next we have to make a question that sigma V is present or sigma H is present. So in case of carbon dioxide, this molecule is a linear, but this plane is perpendicular to the main principal axis, means sigma H is present, means D infinite H point group is present in carbon dioxide. So this molecule is assigned as a D infinite H point group. Another example is the hydrogen. In case of the hydrogen, hydrogen is also linear, means C infinite V or D infinite H point group is present. Now in case of hydrogen, this plane is perpendicular to the main principal axis, means sigma H is present. Horizontal plane of symmetry is present, means point group is D infinite H. Another molecule is hydrochloric acid. In case of hydrochloric acid, it is a linear, and this one is the imaginary axis. It means this plane is parallel to main principal axis. It means sigma v is present, so point group is C infinite V. So dear participant, we have to assign this molecule is a linear or non-linear. Then we have to follow that sigma v or sigma h, and according to that sigma v sigma h we can assign the point group to that molecule. In case of the hydrochloric acid, this molecule is a linear, so C infinite V or D infinite H point group may be present, but the plane is parallel to the main principal axis. It means sigma V is present, so point group is C infinite V. Another molecule is carbon monoxide. In that carbon monoxide, this is also linear, so C infinite V or D infinite H point group may be present, but here sigma V is present because this plane is parallel to main principal axis, so C infinite V point group is present. Another molecule is HBr. So this one is very similar to hydrochloric acid. So here sigma V is present. It means point group is C infinite V. Another molecule is a methane molecule. In case of methane molecule, it is a tetrahedral. This molecule is a tetrahedral, and this molecule consists E 4C3, then 6 sigma D, 3C4, etc. symmetric elements. So ammonia molecule, methane molecule is a tetrahedral. So is a molecule linear or non-linear? Yes, we can say that this molecule is a non-linear. Then we have to make a question that multiple harder axes are present. Yes, multiple harder, it means 3C3 is the minimum criteria to be a multiple harder axis. It means methane molecule consists 4C3. It means multiple harder axes are present in case of the methane molecule. So point group may be TD, OH or N. But in case of methane, sigma D is present. It means point group is TD. So in this case, if sigma D is present, then TD. Sigma H is present, then OH. Both are absent, then N. So in case of the methane, sigma D is present, means point group is TD. Another molecule is SF6 molecule. Now in case of SF6 molecule, this molecule consists E 1, 2, 3, 3C4 and 4C3, sigma H, etc. symmetry elements. So in case of the SF6 molecule, this molecule is a non-linear. It means C infinite V, D infinite H point groups are absent. In this case, multiple harder axes are present. It means we have to go for the TD, OH or NO. But in case of SF6 molecule, sigma H is present. The shape of the SF6 molecule is a octahedral, and one sigma H is present, means point group is OH. Now next molecule is HOCl, or we can say hypochlorous acid. This is non-linear. It means C infinite V and D infinite H point groups may be absent. Any multiple harder axes are present in that molecule. This molecule has no any proper or improper axis. Means there is no question about the multiple harder axis. So another question, any proper improper? No, means point group may be C1, Ci or Cs. Here only this one is planar molecule, means point group is Cs. Point group is Cs. This is trans dibromodichloroethane. Now in this case, this is again non-linear. It means C infinite V and D infinite H point groups are absent in this molecule. Multiple harder axis, so there is no any proper axis is present in this molecule, means multiple harder axes are absent. Then we have to make a question that any proper improper axis, proper and improper axes are also absent, means we have to go for the C1, Ci or Cs. Here the inversion of this carbon bromine bond towards the carbon bromine bond, as well as carbon chlorine bond to carbon chlorine bond and carbon hydrogen bond to carbon hydrogen bond. It means I is present. It means it is assigned as a Ci point group. So this molecule consists Ci point group. Another molecule is C, X, Y, Z, W. This is tetrahedral molecule. It means this molecule is a non-linear. This molecule is a non-linear. It means C infinite V and D infinite H point groups are absent. Then we have to make a question that any multiple harder axis. So there is no any proper or improper axis of symmetry is present in these molecules. Means no. Then we have to make a question, any proper improper axis? No. Then we have to make a question that sigma H is present or I is present? No, both are absent. Then point group is C1. Point group is C1. Next molecule is water molecule. This molecule consists E, C2, sigma Vxz, sigma V, YZ symmetric elements. Water molecule consists E, C2, sigma Vxz and sigma V, YZ symmetry elements. Okay, is it linear? No, it is a non-linear. So we have to make a question that multiple harder axes are present? No, it consists only one proper axis, that is C2. So then we have to make a question that any proper improper axis? Then yes, proper axis. Then we have to go for the proper axis. So Cn does perpendicular to and C2, it means C2 perpendicular to 2C2. The water molecule consists only one C2, it means C2 doesn't perpendicular to 2C2s. It means we have to go for the C option, otherwise we have to go for the D option. Okay, if Cn does perpendicular to the and C2, then we have to go for the D option, otherwise we have to go for the C option. In case of the water molecule, C2 doesn't perpendicular to and C2, means 2C2. It means we have to go for the C option, C2, C2H, C2V or C2D. But here 2 sigma V are present, it means point group is C2V. So dear participant, remember that n is equal to order of axis, so C2 is present, it means point group is C2V. Another molecule is a ammonia molecule. It is a pyramidal. It consists E, C3 plus, C3 minus, sigma Va, sigma Vb and sigma Vc symmetric symmetry elements. Okay. The shape of this ammonia molecule is a pyramidal. It means it is a non-linear. Then we have to make a question that multiple harder axes are present. No, it consists only two C3, that is C3 plus and C3 minus. So minimum criteria to be a multiple harder axis is 3C3. It means we can't consider as a multiple harder axis for this molecule. Any proper improper? Yes, it consists 2C3. It means go for the proper axis. Then we have to make a question that C3 does perpendicular to 3C2. No, C3 doesn't perpendicular to 3C2. Why? This molecule consists only 2C3, means we have to go for the C option. Okay, so C3, C3H, C3V or C3D. But this molecule consists 3 vertical planes. It means point group is C3V. Why? Here order of axis is equal to 3. It means point group is C3V. Another molecule is BF3 molecule. This molecule consists E twice C3, means C3 plus C3, C3 plus C3 minus. C3 is perpendicular to 3 C2s, sigma H twice S3, etc. BF3 molecule is a planar molecule. It means it is a non-linear. Multiple harder axes are absent. Okay, why only 2 C3 are present, means multiple harder axes are absent. means TDOH as well as IA point groups are absent. Any proper improper? Yes. This molecule consists proper axis. So here C3 does perpendicular to 3C2? Yes. In case of BF3 molecule, we have to go for the D option, means order of axis is equal to 3. It means D3, D3H, D3D or D3V. But this molecule consists sigma H. It means point group is D3H. So we can assign D3H point group to the BF3 molecule. Another molecule is benzene molecule. This molecule consists E C6. C6 is perpendicular to 6C2 and sigma H symmetry elements, etc. Okay, according to this chart, first of all we have to make a question that is a molecule linear or non-linear? Is a molecule linear or non-linear? Is a molecule linear or non-linear? Non-linear. Multiple order axes are absent, means TDOH point groups are absent. Then we have to make a question, any proper improper? Yes. Proper axis C6. So we have to make a question that C6 does perpendicular to 6C2? Yes. C6 does perpendicular to 6C2, means we have to go for the D option. So point group may be D6, D6H, D6D or D6V. So here sigma H is present as a plane of symmetry, means point group is D6H. Another molecule is PF5 molecule. The shape of the PF5 molecule is trigonal bipyramid. This molecule consists E 2C3, means C3 plus C3 minus. C3 is perpendicular to 3C2 and sigma H symmetry elements. Okay, so according to this graph, according to this chart, we have to make a question that is a molecule linear or non-linear? Means non-linear. Multiple order axes. Multiple order axes are absent. Why? The minimum criteria to be a multiple order axis is 3C3. So this molecule consists only 2C3, means multiple order axes are absent. Any proper improper? Yes, it consists C3. Then we have to make a question, C3 does perpendicular to 3C2? Yes, C3 does perpendicular to 3C2, means we have to go for the D option. So here order of axis is equal to 3, means D3, D3H, D3D or D3V. So here sigma H is present, means point group is D3H. Another molecule is NiCN4 2 minus complex. NiCN4 2 minus complex. This is quadplanar. This molecule consists E C4 as a main principal axis, C4 plus and C4 minus. C4 is perpendicular to 4C2. So in this case, okay, this is the main C4, 1C2, second C2, third C2 and 4C2. It means C4 is perpendicular to 4C2 and sigma H is present. So this molecule is a non-linear, multiple harder axes are absent, and C4 is proper axis C4 is present. So means we have to go for this option. C4 does perpendicular to 4C2? Yes. C4 does perpendicular to 4C2. Means we have to go for the D option. So here order of axis n is equal to 4. Means D4, D4H, D4D or D4V. So here sigma H is present. Means point group is D4H. Another molecule is trans-dichloroethylene. In case of the trans-dichloroethylene, this molecule consists E, C2, sigma H and I-symmetry elements. So this molecule is a non-linear. It means C infinite V, D infinite H point groups are absent. Multiple order axes are also absent because this molecule consists only one C2. Any proper and improper? Yes, proper axis. Then we have to go for the next question. C2 thus perpendicular to 2C2. So here in case of trans-dichloroethylene, C2 doesn't perpendicular to 2 C2s. Means we have to go for the C option. So C2, C2H, C2V or C2D. But here sigma H is present, means point group is C2H. Next molecule is cyclopentadiene. In case of the cyclopentadiene, E, C5, C5 plus C5 minus means 2C5. C5 is perpendicular to 5 C2s and sigma H is present. So according to this chart, molecule is a non-linear. Multiple harder axes are also absent because this molecule consists only 2 C5, that is C5 plus and C5 minus. Proper axis, yes, this molecule consists proper axis, and in this case C5 does perpendicular to 5 C2s, means we have to go for the D option, D5, D5H, D5D or D5V. But here sigma H is present, means point group is D5H. Next molecule is ferrocene. It consists two isomers, one is cis and another one is trans. This molecule consists E, C5, C5 is perpendicular to 5 C2s and sigma H. In case of cis ferrocene, non-linear, proper axis, C5 thus perpendicular to 5 C2s, means we have to go for the D option. Either we have to go for the D5, D5H, D5D or D5V. But here sigma H is present, means point group is D5H. Now in case of the trans, what will happen? So in this case, E 2C5 means C5 plus C5 minus C5 is perpendicular to phi C2 and sigma H is present. So here this is non-linear, multiple order axes are absent, but proper axis C5 does perpendicular to phi C2, yes. D5, D phi H, D phi D or D phi D, D phi V. So in this case sigma H is present, means point group is D phi H. Next molecule is a naphthalene. In case of the naphthalene, it consists E, C2, C2 is perpendicular to 2 C2s and sigma H. In case of naphthalene molecule, this is one C2, another C2, third C2, and this one is the sigma H. This molecule is a non-linear, multiple order are axes absent, and here C2 thus perpendicular to 2C2 means we have to go for the D2, D2H, D2D or D2V. But here sigma H is present, means point group is D2H. Another molecule is iron pentachloride, iron pentacarbonate. The shape of this molecule is trigonal bipyramid. This molecule consists E 2C3, that is C3 plus C3 minus. C3 is perpendicular to 3 C2s and sigma H. So from this chart, molecule is a non-linear, means C infinite V and D infinite H point groups are absent. Multiple order axes are also absent. Then proper axis means C3 proper axis is present. Then we have to make a question that C3 does perpendicular to 3 C2s, yes. So we have to make a question that D3, D3H, D3D or D3V. So here sigma H is present, means point group is D3H. Another molecule is this is boric acid. In case of the boric acid, this molecule consists E, C3, sigma H. So non-linear, multiple order axes are absent, and C3 proper axis and C3 doesn't perpendicular to 3 C2s, means point group is C3, C3H, C3V or C3D. So here sigma H is present, means point group is C3H. Next molecule is a chloroform. In case of chloroform, this molecule consists E, twice C3, 3 sigma V. This is non-linear, it means C infinite V, D infinite H point groups are absent. Multiple order axes are also absent. So C3 proper axis is present, but C3 doesn't perpendicular to 3 C2s. It means point group is C3V. Next molecule is anthracene. This molecule consists E C2 C2 is perpendicular to two C2s and sigma H. It means point group is D2H. Now next molecule is hydrogen peroxide, planar hydrogen peroxide. So this molecule consists E C2 and sigma H. So point group is C2H. And the last example, non-planar hydrogen peroxide. This molecule consists E C2 2 sigma V. It means point group is C2V. So I think these are the enough examples to assign a point group according to the Swine-Flash method. So dear participants, thank you very much for listening me very silently.